Okay, let me start by saying that I would much rather prefer to be in Montegrotto to do this talk with the old method. But anyway, thank you, Ugo, for giving me the opportunity to present again this work that in these days should be in press in the Journal of Frontiers in Physiology. So, as you see in the title, you will hear again about STIM1, about Orait1, but my presentation has also to do with the tubular aggregates, aging, and exercise. So this is an electromicrograph of an EVL fibers from adult mouse processed with the Golgi staining technique. And if you are lucky, sometime this technique stains also the sarcoplasmic reticulum that here you see in dark. It looks like a little bit complicated, but actually the sarcoplasmic reticulum of skeletal muscle is composed of two main domains. The regions closely associated to the tubules marked in yellow, which are named junctional lesar or terminal cistern. And you see, these regions are darker, actually, are even more darker because they contain calsequestrin, the protein that accumulates calcium in proximity of the sites of calcium release, the ryanodine receptors. And then there is the free SR or the longitudinal SR, which may be located at the A band or at the I band of the sarcomere. Free SR is rich in Cerca pumps, which operate to reuptake calcium after a contraction using ATP. Now, as you heard in Feliciano talks yesterday, the intracellular membranes at the I band between triads and Z lines are capable of significant remodeling during exercise. So briefly, because Feliciano already told about this remodeling involves elongation of the T-tubule into the I band toward the Z line, flattening of SR cisterne, with their final docking with the T-tubules to promote the assembly of new intracellular junctions, which contain Orait1 and STIM1 that we call the calcium entry units. These structures facilitate the use of external calcium during repetitive stimulation. Now, tubular aggregates, abbreviated TAs, represent one other type of sarcoplasmic reticulum remodeling in skeletal muscle. You see, TAs are this abnormal and extensive accumulation of SR membranes, which were first described in 1970 by Engel in human biopsies from dyskalemic patients. In humans, tubular aggregates are found also in other muscle disorders, and they constitute the main morphological alteration in patients suffering from the tubular aggregate myopathy, a disease that, let me say, likely for our work has been recently linked to mutations in STIM1 and Orai1. In a paper we published in the 2012, we have shown that tubular aggregates also form in fast twitch fibers from aging male mice. So in this first part of my presentation, I will try to address the following question. What is the role of STIM1 and Orai1 in the accrual of these SR membranes? Immunofluorescence experiments of EVL fibers from 2-year-old mice, which are rich in TAs, indicated that tubular aggregates stain positive for both STIM1 and Orai1. As you can see in these two panels, A and B, in these experiments, fibers were double labeled with an anti-ryanodine receptor antibody to have a reference mark for the position of triads that you see in both panels in red. So the only difference that you can see if you compare these two enlargements here is that while the staining of STIM1 is very dense and quite uniform, the staining pattern of Orai1 is more variable and kind of patched. If you recall again from Feliciano talk, Orait1 is a calcium channel of external membranes. So to be functional, should be localized either in the plasma membrane or in the transverse tubules. However, we know from literature and also as you can appreciate in these two electron micrographs, here we have an aggregate cut longitudinally, here transversally. You see anyway that the transverse tubules stained with ferrocyanide in dark here, you see is mostly confined at the edges of the aggregates and very, very rare inside. And sometimes you have small pieces like here. But anyway, one possibility is that the tubules membranes are just trapped within the membranes constituting the aggregate without being able to reach their functional destination. And this hypothesis is nicely supported also by functional experiments. Indeed, in functional experiments, we then subjected intact EDL muscle fibers isolated from adult and aged mice to an ex vivo fatigue protocol based on 30 consecutive tetanic pulses at 6 years of frequency and in presence of 2.5 millimolar of extracellular calcium. And the results of these experiments, plotted in panel A as a function of time, indicate that EDL muscle from aged mice exhibit a slightly accelerated fatigue compared to adult. You see this red curve here. And in panel B, the bars show the forceful decrease calculated, evaluated at the 10 tetanus, this point in the experiment. And you see that the decrease in contractile force in aged EDL was about 10%. Now, to verify if this external calcium plays a role in this reduced resistance to fatigue of aged muscle, we then repeated the same experiments, but after removal of external calcium. And now note how EDL muscle from adult mice do show a decay in contractile force when calcium entry is prevented, this curve here in blue. But decay that is not present in aged muscles. So, and as you can appreciate also down here, where again in the bar we show the forceful decrease at the 10 tetanus. So in this slide, I summarize the results from the first part of my talk. I'll show you what? I show you that TAs are both STIM1 and Orai1 positive, with Orai1 probably just trapped within the aggregate, but without being able to reach the tubules. I show you that aged EDL muscle are less resistant to fatigue than adult in presence of extracellular calcium. But when extracellular calcium is removed, the decay in contractile force of adult muscles is much greater than in the latter, than in aged muscle. So this result pointing to dysfunctional calcium entry in the latter. These altogether, these results seems to suggest that the TAs are ordered tubes of SR membranes that accumulate large amounts of STIM1 and Orai1, which are apparently not functional for calcium entry. So what we have done next? We know that SOCI in muscle is very important to limit fatigue. We knew that extreme exercise is able to enhance the assembly of calcium entry units and that the TAs form with aging. So we just thought to exercise mice, and specifically we investigated if voluntary training in wheel cages starting from 9 to 25 months of age was able to counteract TS formation and to improve muscle function. Mice were kept, you see here, in a wheel cages for 15 months in a setup in which mice can run voluntarily, mostly at night. And as you see in the graph on the right, mice run on the average 30 kilometers per month between 14 to 25 to 20 months of age. So practically they run 4 or 5 kilometers per night. At 2 years of age, mice were sacrificed and ideal muscles were processed for structural and functional experiments. And the first very encouraging results came immediately when we quantify in histological sections the number of fibers presenting TAs visible in these images, histological images as darker islands, the number of TAs per fibers, and also the average size of the aggregates. And as you can see in these bar graphs on the right, the percentage of fibers presenting TAs was strikingly reduced from 50 to only 70% in aged muscle following training. Their number per area was their number per fibers was reduced of more of 50%, and the average size of a few remaining aggregates was smaller of about 17%. So the reduction of number and the nice, another nice result is that the reduction of number and frequency was also accompanied by rescue of function. Indeed, when we performed again the fatigue experiments, we immediately noted that the capability of aged muscle to use external calcium was recovered by the training. If you look at these three top panels up here, you can see that now ideal muscle from both adult and age-trained mice do show a decay in contractile force when calcium entry is prevented. Decay, though, that if you recall from the previous slide, was not present in aged EDLs. And again, these two results are significantly, statistically significant, as you can appreciate down here in the bar graphs showing the fourfold decrease at the 10 tetanus. Now, for people that know me, I am mostly an electron microscopy scientist. So these results suggest immediately to us to verify if the recovered capability of aged muscle to use external calcium after training was related also to an increased assembly of calcium entry units. And so to do so, we analyze with electron microscopy again the two main different components of calcium entry units: the number of stacks per area, and also the length of the transverse tubular network at the high band after staining with ferrocyanide. So you see here the two tubules again are in black. Because of this ferrocyanide, it's an electron dense precipitate into the tubule lumen. And again, as you see on the right, both parameters are significantly increased in aged muscle following training. Okay, in this slide, in conclusion, in this slide, I summarize the results of the second part of my talk. I show you that voluntary training in mice is able to reduce the number and size of tubular aggregates, is able to increase the assembly of calcium entry units, but also aging is able to restore the dependence of aged muscle from extracellular calcium during repetitive stimulation. And altogether, this data seems to suggest that at least in mice, TAs may form with the age as a result of muscle inactivity and that their accrual can be strongly reduced by regular exercise. To conclude, I would like to thank the people that contributed, the author of the paper, actually, and especially Antonio Mucolucci for the functional experiments, Laura Pietrangelo that helped me a lot with the quantitative electron microscopy analysis, and all of you for your attention.
My question regards this very interesting story about the calcium entry units and tubular aggregates. I have studied tubular aggregates in two conditions. One was in hypokalemic periodic paralysis when I was with Andrew Engel, and I studied calcium uptake during a period of, during periodic paralysis. And I followed a family that has a Orait1 mutation. So my question is, to Simona, what do you think provoked these tubular aggregates? The lack of calcium, the lack of activity, and what is the function of the ACU? You know, to change this over. You know, I want some explanation about the relationship of activity, ACU, and tubular aggregates.
So my data seems to suggest that these aggregates may form as a result of muscle inactivity. Indeed, if you train
Like
mice, if they train for a long, but we really not know exactly yet what is the relationship between calcium entry units and these aggregates, actually, because tubular aggregates look like more beans of for protein that are
very big.
are produced in a large amount, and the muscle don't use.
Yeah.
Excuse me. The line is interrupted. I cannot hear very well, but I hope I could answer your question.